Yes, continuation of motion in a plane, in that uniform circular motion. Right. What is uniform circular motion? When a body moves with constant speed on a circular path, it is said to have a uniform circular motion. Right. Now we can see like in uniform circular motion, the speed of the body that remains same, right, but the direction of motion which changes at every point, right. Now we can see the different velocity vectors at different positions of the particle. At each position, the velocity vector, that v vector, which is perpendicular to the radius vector, is it right? So thus the velocity of the body which changes continuously, we can say that is due to the continuous change in the direction of motion of the body. So as the rate of change of velocity is acceleration, so a uniform circular motion is an accelerated motion, right. So from this we can explain that angular displacement, the angular displacement and the linear displacement of the particular motion. So the linear velocity is constant in magnitude but changes in direction continuously. So the particle experiences the acceleration, right. So in case of non-uniform circular motion, means what will happen to the particle that experiences the acceleration due to the change in both speed as well as the direction, right. So that we are seeing here, suppose a particle which starts from, we have seen the position P and the position which time which vary, and the particle which covers the distance of what we have taken here, the distance of a dull s, right. So the angle of the revolution that we have taken, that dull theta is the angular displacement of the particle. If r may be the radius of the circle we have taken, means we can say the dull s, dull theta, which is equal to dull s by r. That means we have seen this, that is angle which is equal to, what is the formula? Angle which is equal to arc by radius. From that we got this dull theta which is equal to dull s by r. So the unit of angular displacement is we know that is radian, right. So you can see here the velocity v that turns through the same angle dull theta becomes v dash, we have taken here. So the linear displacement is dull r vector. The linear distance we have taken here, the dull s is the r, right. That only we explained. So we can say that omega, that means the omega. So the angular displacement of the particle in time dull t is the average angular velocity. That is only we have taken the average angular velocity omega vector, which is equal to limit dull t turns to 0, that we can take dull theta by dull t. Got it? So the next one is, we can see the relation between the linear velocity and the angular velocity, right. Now you can consider a particle which moves along a circular path of radius r, and suppose the particle moves from A to B in time dull t and covering the distance of dull s, which is along the arc AB. Then what we said? It is the angular displacement of the particle, we said. So what we know, that the angular displacement, and that the linear velocity is the rate of change of the linear displacement, that we can say that v vector which is equal to limit dull t turns to 0, then dull s by dull t. But we know that the dull s which is equal to r into dull theta. That means what? R into dull theta, that is radius which is equal to, we have taken arc which is equal to radius into angle, that angle which we have taken, right. So that we are applying that value here, v vector which is equal to limit del t turns to 0. Instead of del s, you have written r into del theta by del t. Then we will get v modulus of v vector which is equal to r into that omega, as per our explanation part of the angular displacement, which is nothing but what? So that is del theta by del t. So that is omega. So v which is equal to omega cross r vector, omega vector cross r vector. Got it? So the next one is, we are seeing acceleration in uniform circular motion. See how the acceleration which is in the uniform circular motion we can see. See, the time rate of change of angular velocity of a particle, which is called as the angular acceleration, we know that. So del omega is the change in the angular velocity with time. So the average angular acceleration, as we know, that is alpha, which is equal to del omega by del t. So now we can see that the direction of acceleration of a particle in a uniform circular motion, how it is. See, when a body is in uniform circular motion, the speed remains constant, but its velocity changes continuously due to the change in the direction. Is it right? So that only we said the motion is accelerated, the speed remains constant, which is there in the uniform circular motion. If you understood this are all the things very clearly about the centripetal force, the centripetal acceleration is very easy for you, right? So when a body is in uniform circular motion, the condition, that is the speed remains constant but the velocity continuously changing the direction. So the motion is a accelerated motion. A body which undergoes a uniform circular motion, it's acted upon by an acceleration which is directed along the radius towards the center of the circular path which you are seeing. So it's a center seeking, the centripetal force, which we can call it as a center seeking acceleration too. And also you can consider this particle, the diagram, a particle which is moving on a circular path of radius, we have taken r, and it's from the center, right? And with the uniform speed v. Suppose a time t, the particle is at p, and the time we have taken t plus del t, then the particle which at p dash, it moves to some next position. So we have taken that two positions be the velocities vectors from p dash. It's directed along the tangents at the p dash respectively. So we want to determine the change in the velocity. You can take an external point, the 2 points you have taken, and make you can draw the equal and parallel to that. Then we can make it as like a triangle. So we can apply here the vector which is equal to that, close to the triangle. We have apply here the triangular law of vector addition. Then we will get the value, the 3, that means the any hypotenuse value both sides, right? So if we given the name ABC, which means AB plus BC, which is equal to AC. Is it right? So del t which is equal to 0 and del theta which is equal to 0 degree, then the value which is 90 degree, it means we changes, we have given the different changes. If suppose the del t which is getting varied, then we will get the values, right? And see the magnitude of acceleration of a particle in a uniform circular motion. So in the uniform circular motion, we are seeing the magnitude of acceleration of a particle in a uniform circular motion, which is, so this will helps to determine the centripetal accelerations too. So we have seen that if suppose from this diagram you can take, if the dt or that del theta, that it is moving in the angular acceleration, right, which shows the omega, that is the angular acceleration shows, and we can compare the values of AB by PP dash, which is equal to PA by OP. So from this isosceles triangles we can get the similar values, that is del v vector by del r vector, which is equal to modulus of v vector by r vector. So this will gives the value for the centripetal force, acceleration of centripetal force, that is a, which is equal to v square by r. From that we can get the omega square r. How we get omega square by r we can see. So this we can get by applying the limit del t turns to 0, we'll get del v by del t. So that the acceleration which is equal to, we know that we have taken the value from the before step, the limit del t turns to 0, v vector by r vector into, we have taken the acceleration value del r by del t. So we got the acceleration which is equal to v by r, that means the modulus of v vector by r vector, limits del t turns to 0, you will get modulus of del r vector by del t. So from this only we got the acceleration of the centripetal force v squared by r. So that is, we can write the value omega square r, that means because of v which is equal to omega r. So this gives the magnitude of the acceleration of the particle in the uniform circular motion. So as we said, if we knows and if we got the values from the accelerated particle in the uniform circular motion, we can easily understand the centripetal acceleration we said. Is it right? So the centripetal acceleration which gives, that is ACP, we know that v square by r. Now only we derived, and v which is equal to r omega as we said. So this gives the magnitude of the acceleration of the particle, and also we applied the value v square by r is the centripetal force acceleration, we know that. So we are applying r omega by r, so that r omega square by r. So we simplified, we will get the omega square r. So the centripetal acceleration in terms of the frequency, that can be also we can express. So omega which is equal to 2 pi mu. So by applying the value omega square r, it will becomes 2 pi mu square, 2 pi mu whole square into r, instead of frequency we applied. So that we will get the centripetal acceleration, that is equal to 4 pi square mu square r.